All right. So zoom in and let's go. Okay, so for torque, there are two different types of directions. Okay, well, first of all, torque, our equation is going to be T is equal to the perpendicular force times R, which is the lever arm. Now, there are two different types of directions. There are your clockwise and counterclockwise. So I label them as CCW and CW. All right. So how you how you can figure out what is what or who's clockwise and who's counterclockwise is by when you get or understand where the pivot point is, which is pretty much on these labeled by this little black circle here. Think about the bar or this line as the hands of a clock. So if this is the pivot point, right, for this guy here, and it's going down, that would be like pivot points here, it's going down towards 6 o'clock. So since it is trying to push it right this way, this force is trying to push it this direction. If you push it in this direction, then this time hand, right, would go from 6 to 5 to 4 to 3. Time doesn't move that way. It doesn't move that way. So we're going to say that that is counterclockwise. That makes sense?
Yeah.
All right. So then vice versa. All right. I just do this basically for like any problem. Okay. I find the pivot point, which we can label by a capital P. Some people call it the fulcrum. Same damn thing. All right. So here we have this pivot point, and our line is extended out to the right. So that would be towards our 3 o'clock. The force is going downward. All right, so that would push this time hand from 3 o'clock to 4 to 5 to 6. That is the correct way time moves. So then I would say that this is just clockwise. So now, in the example problem that they had given us, if a force is on a pivot point, then the torque is going to be 0. And we can just cross it out. And why is that? Because, again, torque is equal to force times your lever arm. Lever arm is the distance the force is from your pivot point. So in the video, they show it, right? They put the pivot point on the far left side. So that would be on this 8 Newton force. So they cancel this out. We don't need this guy. And then they have us break this down into, to find the net torque on the object, they have us break it down into finding all the clockwise torque and all the counterclockwise torque. So after that, first thing you want to do is you want to label these dudes. So kind of like the hands on a clock, right? This dude's at P, it's going out to the right. So it's like my 3 o'clock. If the forces are going down, that would push it in the clockwise direction. So since the 8 Newton force is already on the pivot point, we don't pay attention to him. So now the only arrow that's pointing down is the 5 Newton force. So like I would just say, all right, I would start off by just like doing this. 5 newtons over here. Right, well, obviously I would label it first. And then the forces that are pushing it trying to push it in the opposite direction are counterclockwise. So once you've identified them, then what you're doing is you're calculating their torque. So torque is these forces times the lever arm. Little r here. Some different sources, okay, or resources would say that they'll use letter D instead. Same damn thing. Okay, so clockwise torques. There's only one that we have labeled. That's that 5 Newton piece. So this 5 Newton is our force, and we have to figure out what R is. How far is this force from the pivot point? All right, so we have this little arrow here telling us, okay, from here to here is 2 meters. And then from here to here is 7. So we're at a total of 9. And then, all right, an additional 4. That would put us here. So that is where the 13 comes from. 2 plus 7 plus 4 is going to give us this 13 meters worth of distance. All right, so that's our lever arm. And then just multiply out. And you're going to get 65 Newton meters is our unit for torque. Then you do the same thing for the counterclockwise guys. So our counterclockwise torques we labeled as the 9 and 4 Newton force. Okay, so the 9 Newton force is only 2 meters away from the pivot point. So multiplying those together, we get 18 Newton meters. Our other counterclockwise force is this 4 newtons. So at 4 newtons, we are 2 meters and 7 away. So we're a total of 9 meters away. So 4 times 9 is going to give us 36 Newton meters. Now, after you have done that for all your different forces and figured out what torques are being exerted on this, we want to find the net torque. Which is the one, that's going to actually make it turn in a given direction and with how much torque in itself. So I kind of wrote off to the side here. You're always going to, subtract the larger torques from the smaller. So first, we have a total of 65 Newton meters worth of counterclockwise torque. Over here, we have 18 plus 36. So on the counterclockwise end, we only have 54 Newton meters. So what you would do is you take the higher minus the lower. So 65 minus your 54, you're going to get 11 Newton meters. And in which direction? The clockwise had the greater magnitude, so we're overall going to be moving clockwise in this piece. Is that helpful?
Yeah, so with now, because my confusion was the clockwise and the counterclockwise stuff. So I was able to do the second problem. I just didn't know which direction it was going in. So I have the right answers for both. And now the only other thing was the second part with the rotation equilibrium, because it doesn't give you any kind of equation. So I have no idea where I'm going.
Okay, well, I'll walk you through that. All right, so in the other piece, I put the pivot point over here. And then once you use to figure out that this is going 9 o'clock, right? And if the thing was, we're trying to push it downward, it would move from 9 o'clock to 8 o'clock. So any downward force on this one would be your counterclockwise. It's trying to push it up, and that would cause time to move in the or in the correct way. We would call those our clockwises. And then you're just doing the same thing, and you wind up with the exact same answer. So those are your net torque problems. All right, so for this, for rotational equilibrium, the net torque is going to equal 0. So what that means is pretty much this is your equation that you're going to be looking to use a lot. All right, the clockwise torque has to equal your counterclockwise torque. So in this example problem, the pivot point's in the center. So we drop this piece in the center. We call it our pivot point. They tell us that this seesaw is 3.2 meters long. So I just kind of drew this on here. And then it says a girl that is weighing 580 newtons sits at one end. So I arbitrarily just picked the left side. And then they want to know where the hell a boy would have to sit weighing 670 newtons to balance this thing. So in order for these things to equal out, right? So like if you're like on a seesaw, if you're the big sister or brother or whatever, and you're playing with someone that's lighter than you, the lighter person's going to need to wind up going farther away than you do in order to get it to, right, to be flat, to be balanced. So essentially, you have to get your torque equal to theirs. And so they tell us that the girl's sitting all the way at one end. And if the pivot point is at the dead center, 3.2 cut it in half, you're going to get this 1.6 meters. So the girl is got 580 newtons here and has a lever arm of 1.6 meters. So we have one side of our equation. Clockwise has got to equal counterclockwise. So we have the girl on this end, the 580 times 1.6. We get this 928 newton meters. The only thing we know about the boy is his weight, which is going to be the force. All right, so like essentially, I guess it would be all right, but it's like the force of the girl, force of the boy, which is just their weights. So we don't know what this value for R is, or how far they need to be away from the pivot point. But once you know, all right, the torque on one side, you know that the other has to equal that. So if we have 928 newton meters worth of torque on this end, we need to have the same value over here. And if we know his weight, his force, but we don't know the distance, all right, this is basically what you wind up with. 670 R equals this 928 newton meters. Divide out by that boy's weight, and you're going to get a distance here of this 1.385 meters.
I have a question real quick.
Okay.
Okay, so I know how to do the math and everything, but how do I know like which one is, so between 580 and 670, they're both facing down. So how do I know which one's clockwise and which one's counterclockwise?
So same thing with like what we did on the front. If you just drew a clock out real quick. This is the easiest way for me to do it. Pivot point will be here in the center.
Based on where the pivot point is?
Yeah, it's always based on the pivot point. So if that pivot point's in the center and the boy's downward, right? If this is 3, 6, 9, 12. By pushing this hand downward, that would be pushing time in the correct way. So that is your clockwise torque here, your clockwise force or torque being provided. And then the weight over here would be pointing downward. So now I'm looking at it just like this, like basically pivot points here. This would be like the 9 o'clock part of it. And if that's pushing it down, that's trying to make time go from 9 to 876. Doesn't do that. So that's why this guy was our counterclockwise.
Okay, so anything left of the pivot point would be counterclockwise and anything right would be clockwise?
Yes and no. Well, it depends. It depends on, right? So like in this problem down here, I don't want to say anything to the left is clockwise or counterclockwise because it's dependent upon. All right, so this would be like a 9 o'clock piece. This guy, 920 newtons, pointing downward is counterclockwise because it's trying to make it go from 9, 8, 7, 6. But this dude over here is pushing it up. So that is why he's clockwise and this dude would be your counterclockwise.
Okay, that makes sense. Thanks.
All right. Do you need anything on the others?
No, I'm good.
All right. Hell yeah. All right. Where's this?